Hello. Today we're going to talk about some analysis and Simulink optimization of a paper called Accuracy of Analytical Methods for Obtaining Supercritical Transients with Temperature Feedback. So what we're really talking about here is nuclear fission. Nuclear fission is when a nucleus of an atom breaks apart and releases energy. We use that energy to create nuclear power. So when we say supercritical transients, what we're really talking about is the amount of power that is being produced in the reactor is changing, it's going up. And so we say that the reactor is supercritical and the reactivity is going up. And we're specifically going to compare that to temperature feedback and different kinds of temperature feedback. And what that describes is the amount of fissions that are happening and the reactivity of the reactor changes as we change the temperature in the reactor. And a good design of a reactor should have a negative temperature feedback, as we'll see, because that's going to cause you to have fewer fissions when things get hotter. Nuclear engineers use complex mathematical processes to predict what happens in a reactor, starting at the atomic level, and as we've kind of just seen in the previous image, but expanding all the way to include the macroscopic changes throughout a plant that may span hundreds of acres. Some of these plants are absolutely huge, and there is a lot of math involved in putting together all of the different things that change as we produce power. Today we're going to look at one formula that is used to model changes to something that we call reactivity, which, as I described, is basically the amount of fissions that are happening in the reactor at any given time. This is the formula that we're going to be looking at today. So it literally just describes that, and I'm going to kind of go through what each of these components are so that we can see how they fit together. And then Troy is going to show us a little bit of what happens when we change these components. So the first thing we'll mention is reactivity. We've kind of already talked about what that is, represented by rho here in the equation. And it is the fractional change in neutron population per generation, which is kind of a fancy way of saying that it's a way of describing the number of fissions that are taking place in the reactor. We commonly refer to this hand in hand with what we say are the number of neutrons in the reactor, because the number of neutrons directly affects the number of fissions that take place, because the neutrons are what are actually inciting the reactions. Second item we'll talk about is the delayed neutron precursor decay constant. This describes this is the weighted average time for fission product daughters to undergo a beta minus decay and produce delayed neutrons. Delayed neutrons, without getting too much into detail, when you have a fission that happens, we now have not a single atom anymore. We have two atoms that are smaller. And those atoms are usually not stable, and so they'll usually beta minus decay. That decay produces more neutrons. So we have a neutron that might be produced from the initial fission. That's something we call a prompt neutron. And then we have neutrons that might be produced from these what we call fission product daughters. Those are called delayed neutrons. So then I mentioned prompt fissions. We'll also talk about prompt neutron lifetime. Describes the time required for a neutron which is produced directly from fission to cause more fissions. So that's a little bit different from a delayed neutron that causes more fissions. In the formula, we also have the reciprocal of thermal capacity of the reactor. This describes essentially how much heat the reactor is absorbing at a given temperature. Then we have the initial neutron density. This is basically it's a very simple concept of how many neutrons are in a given area in the reactor. Neutron density is proportional to the power output of the reactor. So when we talk about the output of the reactor, one of the ways that we can look at this is just to simply say how many neutrons we have in a given area, or the neutron density. Specifically, n sub 0 refers to the initial neutron density. Temperature coefficient of reactivity. This is the big item that we talked about before. We're going to talk about how this changes the equation, or how it changes the output of the equation. This is a design factor that translates the relationship of reactivity and temperature. Having a negative temperature coefficient of reactivity allows the reactor to be self-limited, because heat generated by increased fissions will cause fewer future fissions to occur. So what we're talking about here is basically something that doesn't run away with a positive. If we had a positive value here, we would see a runaway of fissions, because each fission would then in turn cause more heat, which would then in turn cause more fissions, and that's a very dangerous situation. The last item here is the delayed neutron fraction. This represents how many of the current neutrons in the reactor were born as delayed neutrons by prompt neutrons. This factor is very important when we talk about actually controlling the reactor, because these delayed neutrons essentially give us a chance to actually react to what the reactor is doing. So we have a chance to actually control what's happening by making incremental changes, and then seeing the reactor change what it's doing, and then we can in turn change what we're going to do to operate the reactor. At this point, I'll go ahead and turn it over to Troy. He's going to talk a little bit about the model itself and the graph that we produced.
All right, thank you. So here we have our Simulink model. We're just looking up the equation that we gleaned over earlier. The factors that we're going to be manipulating are the alpha and the beta, so our delayed neutron fraction and our temperature coefficient of reactivity. And so here in this graph, we're looking at a reactor that is in a prompt supercritical position. So we have we're having a change in our reactivity, and it's happening very quickly. So in this condition, our initial reactivity is going to be greater than our delayed neutron fraction. And this creates a situation such that the delayed neutron fraction has a negligible effect on reactivity. And so with the prompt neutrons, they appear in the reactor very quickly. And so without the delayed neutrons to kind of slow down that appearance, or that overall appearance, you get a very quick change in reactivity, which we can see here by the relatively steep curve of the graph. And then we'll compare it with our graph 2. And this graph is a delayed supercritical condition, such that our initial reactivity is less than our delayed neutron fraction. And we can see here a much gradual slope, and this creates a condition where the delayed neutrons now have an effect. They appear much quicker, or much slower than the prompt neutrons. I think the prompt neutrons appear in the reactor about 10 to the negative 14 seconds, and delayed appear about 10 to the negative 5. So almost 10 orders of magnitude difference there. And so yeah, the delayed neutrons, as you can see, make the reactor controllable by slowing down that change in reactivity. And then finally, our last condition is our temperature coefficient of reactivity. Now, when we were initially doing the derivation of our equation, the temperature coefficient was negative. It just so happens that the final equation has it as a positive. So by switching the sign, we get in effect a positive change in coefficient of reactivity. And so here we can see with it as a positive value, we get an exponential rise in our reactivity. And if you look at the ones prior, you can see how it gets very much so above the reactivity gets much larger than the delayed neutron fraction. And we can see that we hit a prompt critical condition, and the reactor will become uncontrollable. The other ones, such in graph 2, had a negative temperature coefficient of reactivity, and we can see how it pushes the reactivity down to a steady state condition. And that will conclude the presentation.